Thank you for another it's great being here, and I still have some seconds. Oh, no longer. So the starring role in my talk are going to be the root polytope and the Germans from the region. And I'll try to carry it mostly through examples. So on the left here, or yes, it's on your left, you see the root polytope. This is a full root polytope. And let me define it for you. You take a origin and all the positive roots, so EI minus EJ are less than J, and take a convex hull. Okay, so you can just think of this as a root polytope for now, or you can think of the root polytope arbitrary convex hull of roots, some roots, and perhaps the origin. And on the right here, and I will explain later, is a corresponding transfer dehedron. So I claim that this guy corresponds to that root polytope. What is a transfer dehedron? It's again a polytope, and now the edges are parallel to directions. So here's an attempt at explaining in what way. So what we see here is a triangulation of the root polytope we saw before. It's into simplexes, you cut it up into simplexes. Each simplex has the origin as one of its vertices, and three other vertices as well. And so the way we encode one of the simplexes is by a tree. So the vertices are E1 minus E2 corresponding to this edge between the first and the second vertex. So you can this red thing for now. E1 minus E4 is this long vertex between the first and the fourth vertex. And E3 minus E4 is this. So in this way, we can encode our triangulation, this particular one, with trees. Indeed, we can encode any triangulation with trees. The trees will be different. And then to each, now we can zoom onto the tree and look at its right degrees. What do I mean by right degree? Those are the red vectors here. I look at the vertex, I look at all the edges going to the right, it is showing. So there's two edges coming from here, 0 edge going to the right from this one, and 1 edge here. The last one is there's always 0, so we drop it. We can think of these vectors, 1, 1, 1, as integer points in space. And if we plot all of these five integer vectors, right degree vectors coming from these trees, we get exactly the integer points, all the integer points of that generalized vertihedron. We can then also encode this in a polynomial, refer to it as a right degree polynomial. You can also think of it as the integer point enumerator of the generalized vertihedron we just talked about. So each of these trees, these 2, 0, 1, will be x1 squared, x2 to 0, x3 to the first. This slide has way too much to explain, so I'm going to assume that you know Schubert polynomials, and if you don't, then think of Schubert's and their generalizations, the Schubert polynomials. The Schubert polynomial, well, one example is right here. You know, it can be picked up combinatorially from these beautiful pi rings. What this picture is trying to appeal to is that actually these pi rings behave the same way as our triangulation of the root polytope from before. And that's highlighted in the equation here. So the main takeaway is that actually this Schubert polynomial, in this case, is really just a very simple transformation of the right degree polynomial so, or the integer point enumerator of the generalized vertihedron. You can think of it also geometrically as translating into your polytope. And theorem de la Escobar states that there's something more general than just this for one permutation, albeit for only a relatively small class of permutations. From there, you can right away see that really these Schubert polynomials live on a generalized vertihedron. They saturate all of its points. And that was a conjecture in work of Michael and Young, and we can prove that it's true generally that the Newton polytope of the Schubert polynomial is a generalized vertihedron, and it's also saturated. So for each integer point, you do get monomial with non-zero, determined a non-zero coefficient. This picture is trying to illustrate some of the proof. Of course, there's zero time for that, but it's just saying that this Newton polytope will be an Minkowski sum of natural polytopes, and that we can be held from the Rother diagram if you know those. This is the last slide, and it's asking the question of, well, okay, we know the support of the Newton of the Schubert polynomial to be a transportation, but what about the coefficients? So we can embellish the integer points into coefficients and wonder how they behave on this Newton polytope. And that's the theorem, Jacob Matherian, who's here, and Avery St. Cyr, who's also there, which says that actually these coefficients are log concave in the directions. And with that, happy birthday, Richard. I'm a lucky person who gets extra time. Does everyone love my theorem?
Introduce yourself. Normally everybody can say their name.
Hi, I'm Karola Klivans. I make Sarah very happy. So in preparing my slides, I thought a little bit about what I did at Stanley at 60 and Stanley at 70. So it's nice to reflect on the different things and what you're thinking about over time. I'll say that I did have a nice open problem at Stanley at 70 that's still open. So if you'd like to hear it, I'd be happy to tell you about it later. I also thought that I would start with an integer sequence, which was favorite. So name that sequence, 30, 10, 6. For me, it's the successive number of minutes that I've been given to talk. But you can put it into OEIS and you can find it, and before you cheat at the end of the 6 minutes, ask yourself, are you the author of this sequence? Because 2 of you are in the audience. Okay, so one of the prompts that we were given in the 6-minute slides was to talk about what you've been up to. So I thought about what have I been up to in the last 10 years. I thought a lot about the combinatorics of simplicial complexes. So on the left, you see a non-partitional Cohen-Macaulay complex. So sorry, Richard. And on the right, you see a picture from ship firing. And I've spent a lot of time thinking about that. Happy to talk to anybody about that at any time. And if you're interested, I wrote a book. It's on my website. Feel free to grab it. But I was also thinking that I've spent the last 10 years in an applied math department, which is somewhat distinctive in this audience. And so I thought I'd talk a little bit about how Stanley-style combinatorics really does have a place in conjunction with other fields. So you can talk to non-mathematicians. So one place there is in physics. We're no strangers to mathematicians talking with physicists, and we'll see some of that already in other talks this week. I found an interesting intersection in the theory of supersymmetry, and in particular looking at some objects called adinkras, which represent how bosons and fermions might interact with each other in this supersymmetric world. And if you're interested in learning about adinkras, there's a paper, Adinkras for Mathematicians, and it's written by a Stanley student. So indeed, this is already a nice setup there. But something that I've done more recently is think about how multiplets of these particles interact and are reflected in the geometry of the permutahedron. So really coming into sort of the sweet spot of things that we like to think about. My timer is off from the time of the computer. I was too early. So another area is optimization. Again, no stranger to combinatorics, but it is fun to be an algebraic combinatorialist and work in the field of optimization. Here on the left, you see a picture of a very nice convex, not quite polytopic object. And the interesting thing about it is that its vertices are indexed by partitions with a certain number of parts. And so thinking about it with that hat on, one can describe iterative algorithms over these kinds of convex bodies and use that as a way to develop cluster
clustering algorithms. So on the right, you see honest to goodness data and an application of thinking about it on the left-hand side and then moving it back to the right-hand side so that you have some hopefully semantically meaningful pieces of data by thinking of it as nothing more than partitioning some sets. The last applied direction that I'll talk about is brand new for me, and it's thinking about neural networks, and I don't mean in AI, but I actually mean in your brain. So this is a neuroscience collaboration, and thinking about threshold linear networks. The image on the left is by colleagues, not by myself, who have started this agenda. But on the right is a picture of thinking about how oriented matroids come into the story in a real way by thinking about thresholding information and understanding dynamics through the geometry of oriented matroids. So I think there's a lot of promise, and there's even something now called the neuromodulation chirotope that one can look at and feel as though we have accurate toy models of how some activity is happening in our brain. And now for my last slide, I want to say that if I have not thrown out enough keywords for you yet, here are a few more. And really these are things that my group likes to think about. So Richard has given us a wonderful community and family. I'm happy to be adding to it. So my group can wave. I have lots of, and you guys right here behind Richard, don't miss her either. Please say hi to them and ask them what they're doing. They are great people doing interesting things. And I'm excited that they'll be your next generation. And in case you forgot, don't forget 30, 10, 6. Igor, you're one of the authors. And Sergi, I don't know where you are. There you are, you're one of the other authors. So you can ask them what 30, 10, 6 counts.
What's the next number?
So on my last trip through the Phantom's whole route, I met up with my old friend, the mathematician, and the first word out of his mouth were not, "Hi Tim, how are you doing?" but "Someone has ripped all the labels off my irreducible characters in the symmetric group." Now, if you don't know what irreducible characters in the symmetric group are, then you should run, not walk, to your nearest copy of EC2 and read up about it. And if you didn't recognize my illusions with Phantom Toll Booth, that's another book you should read. So for now, just think of an irreducible character as a machine that takes as input the partition mu of some fixed integer n, shown in red here, and outputs an integer according to a certain rule. And there's a whole family of these irreducible characters, and they're indexed by partitions lambda of n. The mathematician had a whole warehouse full of these machines, and they're all carefully labeled in green. But alas, some vandal had come in and ripped all the labels off these irreducible characters, so he was no longer able to distinguish one of them from another. So he asked me and my co-author Jennifer Paulus for some help in being able to restore these missing labels that had been ripped off. Now, this problem is not that hard in theory, at least if you know the value of n, which I'm always going to assume you do know, because in principle you could just go through all the possible input partitions mu, tabulate the outputs, and then compare the results against your favorite computer algebra package and restore the labels that way. That works, but that's very inefficient because, first of all, there's a whole lot of input values you can try, constants of the root n, in fact. And then it's also true that for a lot of those input values, it takes a long time for the answer to pop out. It's high computational complexity. So what you really want is an efficient algorithm that uses as few inputs as possible and has low computational complexity. So the good news is Jennifer and I were able to solve the mathematician's problem. But in order for me to tell you a little bit more about that, I have to say more about what irreducible characters are. So irreducible characters can be computed in terms of these combinatorial geometries called border strip tableau. So the border strip tableau is a Young diagram filled with integers that weakly increase across rows and weakly increase down columns. And such that for every integer, the boxes containing that particular integer form what's called a border strip. So a border strip is a connected set of boxes such that the rightmost box in each row is directly beneath the leftmost box in the row above. So for example, this rightmost 2 in row 2 is directly beneath the leftmost 2 in row 1. The Murrahan-Nakayama rule tells you that the irreducible character indexed by lambda, evaluated at mu, is given by some sign sum over all border strip tableau of shape lambda and type mu. So type mu just means that the parts of mu give you the lengths of the border strips. And don't worry about the sign right now. What I just want to emphasize is that if there are no border strip tableau of shape lambda and type mu, then this is an empty sum and the character value is 0. So that's important. So for example, let's take n equal to 8. And let's take as our input value mu equals 8, meaning the partition with one part of size 8. And if you think about it for a moment, for most shapes lambda, you just can't fit a border strip of length 8 into it. It's just too big. Unless lambda is a hook. Lambda is a hook, then the character value is plus or minus 1, but if it's not a hook, you're going to get an empty sum and it's going to be 0. So that's kind of nice. So you can tell just from this one input value whether lambda is a hook. And if lambda is not a hook, then you can try the input 7 to 1. And by similar reasoning, you can show that you're going to get 0 unless the length of the longest hook is at least 7. And more generally, there's this proposition that if you try this sequence of inputs, n minus 1, 1, n minus 2, 1, 1, and so forth, then the first non-zero value you get in that sequence, non-zero character value you get in that sequence tells you the length of the largest hook. So that's the first step in our algorithm. I'm not going to go through the whole algorithm, but just to give you a sketch, there's a forward pass and a backward pass. So in forward pass, we use ideas similar to the ones I just described in order, and you can recover the principal hook lengths of lambda one at a time, starting from the outside going in. So a principal hook just means that the corner of the hook lies on the main diagonal of the down diagonal. Now, once you've got the principal hook lengths, that's a lot of information, but it doesn't tell you everything because it still doesn't tell you for each hook how many boxes are on the arm versus how many are in the leg. So there's a second pass where we recover the arm lengths and leg lengths starting from the inside out. And this part of the algorithm is complicated to describe in words. It takes up most of our paper, but fortunately it has low computational complexity. Anyway, our main result is that this algorithm works. And in the worst case, it takes only about n to the 1.5 inputs, which is a lot better than constant to the root n. That's actually not the end of the story. There's been an improvement by my colleague Alex Miller at the Center for Communications Research, and using a little bit more character theory than we did, he was able to reduce the number of inputs to n. And again, these values are easy to compute values of character. And that's not the end of the story because n is almost certainly not optimal. As far as I know, the answer true minimum number could be as low as log n, or maybe even constant. I mean, if you think about the hook length formula or hook length formulas for skew shapes, you might think that you could possibly get away with close to a constant number. Don't know how to prove that, but I hope some of you will be tempted to try to improve our results. And so the next time the mathematician has this vandal, we'll be able to solve this problem even faster. So happy birthday, Richard, and thank you.
Apparently the vandal was from Fictionopolis.
All right. So hopefully you all remember my talk from 10 years ago because I'm going to pick up right where we left off. So actually, 9 years ago, my career took a rather unexpected turn into administration. And so I've been Associate Dean of Natural Sciences for 8 of those 9 years. I was interim dean for one of them. And somehow I've ended up in 2 non-consecutive years as interim chair of computer science. That one's definitely ending after this month. And actually, I just found out last week, this one is in doubt because I have an interview for a vice provost position next week. So we'll see. I might not have any time to do any math for the next 10 years. But all this is to say that this is why I haven't been writing books or publishing in journals. All I really have time to do is ask the questions, not really to answer them. And so in about 5 seconds here, we're going to see where I've been asking questions. So I've written a lot of questions for competitions, and this is in part inspired by Richard, because I remember when I was in that 18S34 math problem solving seminar, one of the more interesting handouts we got was problems that you had written for the Putnam exam, even though they hadn't used them. But there were some great questions in there. And so one of the things that I hopefully have done while learning from Richard in is sometimes just asking interesting questions, not even research level questions, but just getting students to think about questions can be a valuable exercise. And so I've written for various competitions at the middle school and high school level. And what I want to talk about today is some of the problems that these students have encountered. And most of my title is subversive combinatorics. The idea is I want to get them thinking about some really advanced topics without knowing that that's what they're doing. They think they're just solving problems quickly. And for example, math counts as a middle school competition. And you might notice these three questions that they solve in the course of a couple of years are something that probably most people in this room know how to do. Now, of course, middle schoolers don't know the Hook-Length formula. They never heard of standard Young tableau, most likely. But these were about 9 or 10 years ago. So students might be in grad school now. They might be taking a graduate level algebraic combinatorics course and seeing standard Young tableau and Hook-Length formulas. Oh man, I wish I'd known that 10 years ago. I had to just write them all up by hand, right, to find all the various cases. But this is showing them, that you don't have to know all the advanced math in order to do some of the computations that go into doing the more advanced work. All right, something that was a little more overtly theoretical, and this is to fit it all on one slide. I realize the text is very small. ARML is a high school competition. That's actually where I was last week, and why I just got in here last night. There were about 2,000 students around the country who participated in this competition, and in 2018, working in teams of 15, they spent an hour working on basically reproducing a chapter from my thesis, which was an answer to a question that Von Knuth had posed in a talk at MIT in the early 2000s. And so they were exposed to binary partitions, so integer partitions where all the parts are a power of 2. Partial ordering is correctly defined for them here, class diagrams, and then getting into a graph theoretic question of if you do have a hexadiagram for the parts ordered set of binary partitions under a certain ordering, does it have a Hamiltonian path from graph theory? And the answer is yes. And actually, if you're curious, it turns out that we don't have time to talk about it right now. But it also occurred to me, though, I've been delinquent. When I was looking for problems involving Catalan numbers, I couldn't actually find very many. In fact, there's one that I submitted for math counts that they didn't end up using, where I just went ahead and gave them, hey, this is what Catalan numbers are. And so at your 90th birthday conference, I'm going to have to present how I've introduced Catalan numbers to younger and younger students over the years. Of course, we know that lattice paths are one way they arise. This problem actually has nothing to do with Catalan numbers, though. This one looks like it would be one of those where it's, oh yeah, it's like A plus B choose B, but it actually isn't. It's actually a problem about integer partitions and a special case of the subset sum problem, which is NP complete. And so this is my way of hopefully trying to get a student to win the $1 million bounty on that and split it with me, but I haven't happened yet. But the other thing that I've done, even before the last 10 years, is working on research projects, not just with undergrads, but with high school students as well. So these are various titles of projects that have gone on to win some recognition. All of these were done by high school students. And actually, the very last talk, thank you for reminding everyone what the Murray-Nakayama rule is and all that. Character tables of the symmetric group can be done. Actually, Sarah Billy introduced me to that as an undergraduate research project where I did not know a whole lot of representation theory, but hey, I could work with partitions and their diagrams. Let's see, this is pretty Lightning partition. Of course, it's a large part of my work as a grad student. This is one of my favorites is when you let high school students name a topic, right? On the related prime time, really long thing. The publication that came out of that was actually called Gold Box Pigeonhole. So when we published it, we only used 2 words. They used a bunch more. But anyway, hopefully I've introduced combinatorics to the masses, and now it's someone else's turn.
I think so. In this talk, we will talk about permutations which are of like n, but they are the product of 2 maximal cycles. So P and Q are both cycles of length n, and we multiply them together. And there's a story here from 10 years ago or so. I had a conjecture that in such a permutation, the probability that 1 and 2 are in the same cycle is exactly 1/2 if n is odd. And Richard proved it. So this would be converse of the usual thing, because usually the advisor has a conjecture and the student proves it, and the student has a conjecture and the advisor proves it. So anyway, we with Boris have we looked at the probability that the cycles of such a permutation, the product of two maximal cycles, come from a given set of positive integers. So if a set is not in A, then there are no such cycles. And we have these two formulas, which are not horrible. And the first one is for the probability that in the product of two maximal cycles, every cycle length is even, and the second one is that every cycle length is odd. And for odd, you have to distinguish the odd and even end cases, because it's possible to have all odd cycles if the whole permutation is like odd or even. Now, this is interesting for its own sake, and Boris is only interested in this for its own sake. But I'm interested in the applications, which are very surprising. So this ties into Phil Hanlon's talk that by solving the conjecture, Richard really helped to connect two remote-looking areas, and I can't wait for the slides to move. So there are two biologically motivated sorting algorithms: block interchange sorting and block transposition sorting. Oh, good. So block transposition is the first one. You have a permutation, and you two adjacent strings of entries, like 5, 6, and 1, 3, 9, and you move one in front of the other. Whereas in a block interchange, it's the same thing, but the two blocks do not have to be consecutive. And in both cases, we ask how many such moves do you need to turn a given permutation to the identity. It's not hard to prove that if you can measure the distance from somewhere to the identity, that's equivalent to being able to find the distance between any two permutations. Now, interestingly, the second one is much better understood than the first, even though that seems to be the more complex operation. On the first one, most questions are still unanswered. Again, I can't wait for the switch. Okay, so anyway, yeah, the cycle graph is then the main tool that connects this to the theory of permutations, which are products of two maximal cycles. So for each permutation, you create a so-called cycle graph, which is not the usual cycles of the permutations, but it has two colors of edges, black and gray. In the black ones, everybody is connected to its preceding neighbor, and in the other, with the gray one, I is connected to I plus 1. It's a directed graph, and it is a unique decomposition into alternating cycles. And crucially, there is a bijection from the set of all permutations in the symmetry group, for which this graph has k alternating cycles, to the set of permutations of in Sn plus 1, which are the product of two maximal cycles. And this bijection preserves the cycle lengths. So if in the cycle decomposition of the directed graph there were only odd cycles, then in the product of permutations there will be only odd cycles only. And then there are two theorems which will make all the knowledge applicable. The first one is the block interchange distance of any permutation from the identity is exactly that. So we exactly know what this is. It's n plus 1 minus the number of cycles in the alternating cycle decomposition divided by 2. On the other hand, for the block transposition distance, that's not as well understood, we only have an upper bound, namely that the block transposition distance is at least that much, n plus 1 minus the number of odd cycles in that cycle decomposition over 2. Again, the cycle decomposition is the cycle decomposition of the cycle graph, which is in close connection with products of maximal cycles in permutations, which are one longer. So if we can say something about when every cycle is an odd cycle, or when no cycle is an odd cycle, then we can say something about this bound, and also we can compare it to the other bound. And we did just that with Boris. So we have two theorems, one for each. One is that how can it be that the block transposition distance, the weaker one, is as much as is equal to the block interchange distance? Well, that can happen only if in the cycle decomposition every cycle is of odd length. In other words, And in the product of two maximal cycles, every cycle is odd. And from those formulas, we can prove that that's asymptotically at most this much. So it's 1 over constant times square root of n. So in all other cases, the block interchange distance is smaller. The other one is what happens when all cycles are even? Then the block transposition distance is at best the worst case. It's about n plus 1 over 2, which nobody can show a permutation is worse than that. And that happens because the partition at least 1 over square root of times. So quite a lot of permutations are as bad as the worst case. Thank you.
Colin, this is joint work and Trank and others. The motivation is to study graph families that are characterized by their degree sequences, which are non-increasing sequences of non-negative integers. They can be represented by Ferris diagrams, as in the example, where you see 6, 5, 2, 2, 2, 1, 1, 1. Following Maris and Roki, we divide the diagram, the Ferris diagram of the partition at the main diagonal into A applied to the upper right and B applied to the lower left. And our focus is on split graphs, which are graphs that you can partition the vertex set into two things, clique and an independent set. So clique has all possible edges and the independent set has no edges. I thought the slide would go. All right, so, okay, all right, so we did that partition into A applied and B applied, so this provides a natural way to divide partition pi into two partitions, alpha pi and beta pi, where alpha pi is the number of squares in each row of A pi, beta of pi is the number in each column of B pi. In this example, we have pi is 4, 4, 2, 2, 1, 1, alpha pi is 4, 3, and beta pi is 5, 2. Note that alpha pi and beta pi are partitioned into distinct parts. Why is that? Because it's a Ferris diagram. We've ordered the degrees by not increasing. So the ends of the rows can't be, the ends of the top row have to happen to the right of the one on the bottom. So therefore, the staggered starts means that the partitions are distinct. All right, so if you've got that, you're good for the next slide. But the next slide is going to be a bit more intense. Here we go. So the complement of a graph has the same vertex set and the complement of the edge set. With Tantan Jai, we show that the union of the parts of alpha pi and beta of pi complement is the set 1, 2 through up to n-1 for a graph with n vertices. How do we do that? We rotate the diagram, the n by n-1 diagram, 180 degrees. The blue squares are where we divide A of pi and B of pi, but now you'll see that the blue squares, when we do the complement over here on the right, are the ones where we start the column for B of pi bar. So in both alpha pi and B of pi bar, the row or column starts at a blue square. Now look at the last square of a column of B of pi complement, which is over on the left, and I put a circle in the square. The parts of alpha pi to the left are shorter because when we count the squares back to the blue, we have fewer. And the parts of alpha pi above are larger because of the staggering. So the part size does not occur in alpha of pi. All right, so that proved the theorem. And we went on quickly to the definition of majorizing. So if we have two partitions, then the pi majorizes sigma if the sum of the parts of pi is equal to the sum of parts of sigma, and the partial sums of pi is always greater than equal to the sums of parts of sigma. We say it's weakly if we only have a partial sum condition and not the actual equality. Then this is interesting for graphs because a partition is the degree sequence of a graph if it only has the beta of pi weakly majorizes the alpha pi and the total number of squares is even. Or if we're looking at split graphs, beta of pi majorizes alpha pi, and if we look at threshold graphs, which is a subclass of split graphs, then they're equal. Beta of pi equals alpha pi. So these are some interesting well-known results, and show the kind of fascination by Maris and Roki, especially show the fascination of how we're doing the split into these two things. Now, amphoras are ceramic vessels used to ship liquids over the Mediterranean Sea, such as olive oil and wine. Those were the big products in those days. They were designed to be leak-proof with a heavy pointed bottom. They also work to keep the load inside the ship from moving around during the voyage. And amphora in a partial order, which Anne and I and another co-author find is, given a poset, a sub-poset P is an amphora if you take all the elements between a pointed bottom, which is one element X, and a broader top, which is an anti-chain A. Then I got this great picture from Diana Tweed on the web. You can see how the amphoras are pointed on the bottom, and then they stack together so they don't move around when the ship is sailing. Just one more slide. Some of the slides should have been a minute and a half, some of them should have been. There we go. So take S block event. So S block event is we take the pair of our two partitions, alpha and beta. So then we order the pairs, alpha, beta. Alpha 1, beta 1 is greater or equal to alpha 2, beta 2. If alpha 1 majorizes alpha 2 and beta 1 is majorized by beta 2. Our theorem with Rebecca Whitman is that adding the top and bottom to the pairs corresponding to degree sequence of split graphs is a lattice that can be naturally partitioned into amphoras. In the example, for split graphs with 10 edges, the blue and yellow amphoras represent different types of split graphs. And each yellow amphora, which you may not be able to see, but each yellow amphora is further partitioned into amphoras by the colors. So there are also amphoras for other types of graphs related to split graphs. And so we think it's an interesting concept, but we'd like to know if other people have seen any use for it. That would be very interesting. If you have a use for a poset which has a broad top and a pointed bottom.
I'm going to describe a generalization of De Bruijn sequences. Let's quickly review De Bruijn sequences. Here's all the 3-digit binary numbers. Here's a cyclic sequence that has all of them. 0, 0, 0, 0, 0, 1. Some of them wrap around like 0, 1, 0. Instead of 3 digits, you could do k digits. So a k letter string is called a k-mer. Instead of binary, you could do base q. How many are there? This was solved in 1894 and I'm promptly forgotten. And then De Bruijn rediscovered it in 1946. And then Richard Stanley rediscovered that there was an 1894 paper in 1975. So I'm going to do a generalization of this. That went way faster than I understood. We're going to look for each k-mer to occur twice instead of once. So here we have a 0, 0, 0 and an overlapping occurrence of 0, 0, 0. Here we have two copies of 0, 0, 1. 0, 1, 0 in the middle by itself and 0, 1, 0 wrapping around. You can verify that all of them occur twice here. And then you could also do it for occurring multiple times. So it could occur m times. The length is k, the base is q. I worked out how many such sequences there are. So they're called a cyclic multi-De Bruijn sequence. And here's a formula for how many there are. And here's the paper that shows how to come up with that. So this made use of associating the sequences with cycles in a graph and counting those cycles using the best theorem. So here's a generalization of the De Bruijn graph. This is the multi-De Bruijn graph. So here our k is 3, k minus 1 is 2. We make vertices out of the 2-digit binary numbers. Then we make edges for each 3-digit binary number. If you take a 3-digit binary number x, y, z, that's going to give you an edge called x, y, z that goes from vertex x, y, vertex y, z. So 0, 1, 1 goes from 0, 1 to 1, 1. You want it to occur twice, so there are two parallel edges like that. You go through your cyclic sequence, reading off each 3 characters, generating a list of edges. You follow that sequence of edges, 0, 0, 0, 0, 0, 0, and so on. And that traces out a walk in the graph that turns out to be an Eulerian cycle using every one of these edges exactly once. And then you can count those cycles using the best theorem and Mobius inversion. While I was writing this up, unfortunately, somebody published something that sounded kind of similar. And different notation and terminology. And also very fortunately, different numbers. So he did not have a closed formula, he had a construction. He performed the construction just for 3 sets of parameters. And so then it's like, did I do it wrong? Did he do it wrong? So I realized that so these represent certain 16-digit binary numbers, these represent certain 32-digit binary numbers. You can just loop through all of them on a computer by brute force, see, do they meet the condition to be a multi-de Bruijn sequence, yes or no? And that verifies my numbers. So I was happy about that.
You're not competitive, are you?
All right, so here's another generalization. We're going to use multiple cycles instead of one cycle. So we have a restriction on the cycle. This is an aperiodic cycle. It has length 4. All 4 rotations of it are different. This one is a periodic cycle. It has length 8. If you do the 8 rotations, some of them are the same. These 4 characters equal those 4 characters, you get repetitions. A multi-cyclic sequence is a multi-set of these. So here's an example, and you can write it like you write permutations in cycle form. And there's multiple ways to represent it. You could have the cycles in a different order. You can rotate the cycles. Reading off these k-mers is a little bit odd because you can wrap around and reuse characters. So 1, wrap around 001, wrap around 001. You can read off 7 characters cyclically starting there. So using that, take this sequence and we do a de Bruijn property with it. K is 2 here instead of 3. Here are all the 2-digit binary numbers. 0, 0 in this cycle by wrapping around reusing it. Another 0, 0. 2 0 1s, you can verify they're all there. So they occur in there twice. So this problem was proposed for just 1 time each in 2012, and they came up with a formula. I generalized it to M copies, and this uses something called the extended Burroughs-Wheeler transformation. It's a data compression algorithm in computer science. And it's also apparently equivalent to something that Ira Geffel did in 1983. So it's all in this paper, and thank you.
Yeah, I want to thank the organizers to give me the opportunity to
Hold the mic 1 inch from your mouth. Yeah.
Thanks. Yeah, for the chance to Pecha Kucha is what we're doing here. But, it's been a great year. I had a sabbatical, and in the spring I visited San Diego. I had to talk with Brendan Rhodes, and we talked about Q Ehrhart theory. So let me just remind you what Ehrhart theory is about. And yes, there is a Q analog. So it's about lattice polytopes, like this lattice triangle. Lattice just means its vertices are on the integer lattice. This one has 4 points, so I put that on a 4 times t to the first. I dilate it by 2, and then there's 10 integer points inside. I make that the coefficient on t squared. They triplicate it and take 3 times the polytope. There's 19 points. And you create this generating function. We'll call it the Ehrhart series, EP of t. And Ehrhart said, oh, it's nice. It's a rational function. This can be a Q analog. How do you take the Q analog of the number of lattice points? Well, we've got any points in RD. Look at their, as an affine variety, a zero-dimensional affine variety, look at their coordinate ring. It's inhomogeneous, but you homogenize it in a certain way. You take an initial ideal, which is you take all things in the ideal, take their top degree forms, get the coordinate ring for a fat point. That ring has a Hilbert series. That Hilbert series is your Q analog. Too fast, I know, but Macaulay 2 can compute this for you for any set of points, and it's actually got very fast algorithms for computing for any set of points. I've been amazed, actually. There's multiple ways to do it in Macaulay. Some are incredibly quick. So there's our Q analog for the number of points, and now, you know, the Ehrhart series had this very nice form. Let me remind you about some of the things that happen there. So the classical theorems, you know, they came from Ehrhart and Ian MacDonald, who sadly passed away last year, and Richard, They say things like, oh, it's a rational function with this denominator, 1 minus t to the dimension of the polytope plus 1. Ehrhart-McDonald reciprocity, it says, if you take that series at 1 over t, it actually has to do with counting integer points in the interior of your polytope dilate. And Richard has a nice, it's called Stanley's reciprocity formula. It's much more general. Richard showed that the numerator coefficients over that denominator are non-negative. It's highly non-trivial. And when you have lattice simplices like that triangle, there's even a generating function interpretation for the numerator, so it's non-negative. And these are the kinds of things we would like to see happening in our Q analog. And conjecturally, some of these things happen. We're still trying to understand why it is. So yes, let me say how these things analogize. Well, it still seems to be a rational function. When I take this Q analog polynomial, it says my coefficients, they're the Q. It's still a rational function in T. Now we've got 1 minus Q to the AI, T to the BI exponents here on the Q's and the T's, and it can be bigger than 1s. And there's a Q Ehrhart reciprocity in which you take 1 over Q and 1 over T as arguments, still have to do with the interior of the polytope dilates, but there's a Q to the dimension of P that sneaks in there. That non-negativity is harder for us to generalize. But for lattice simplices, again, looks like that numerator, you can pick the denominator so that the numerator is, again, a non-negative polynomial, and you don't yet have an interpretation for that, unlike the classical case, even conjecturally, it's all conjectural. But here's the method of proof that we would like to use. People who know Ehrhart theory know the valuative property of Ehrhart polynomials is one way to prove many things. It doesn't work well here, it's not valuable. But Richard has a beautiful other technique. Consider this ring, this affine semigroup. Take your polytope at level 1 and 1 higher dimensional space, 2 times at a level 2, 3 times at a level 3. You create this ring in which the addition of the vectors is the multiplication of exponents on the monomials. So that's a finitely generated algebra we were on in the 19th century. And this is a Cohen-Macaulay ring. Hoxter knew this. Richard and Danilov had identified what is its canonical module. I'm not going to Pecha Kucha the definitions of those things, but the point is the reciprocity comes from this, the non-negativity of the numerator from this, the rationalness from this. We have something that we call the harmonic algebra, which we hope will play the same role. But even the existence of the harmonic algebra is not obvious. So there's harmonic spaces for each slice of points at each level. Harmonic spaces are, for people who know it, Collian systems for those grading rings. There's subspaces. They have to multiply together from this level and this level. They have to multiply to give you something in the addition of the 2 levels. That's not obvious at all. But we proved something that's surprising. It's a little more general. Take a point configuration, another point configuration, and take their Minkowski sum. These harmonic spaces, one times the other multiplies into that one. And it's a non-trivial proof. So I just want to say thanks to the organizers and happy for